Wolves exist across a wide range of environments, from boreal forests and alpine valleys to temperate grasslands and river basins. In each of these landscapes, they occupy a consistent ecological position, not as isolated hunters, but as a regulating force embedded within a complex system of interactions. Their presence influences how energy moves, how space is used, and how other species adjust their behavior in response to risk. In ecological terms, wolves are often classified as apex predators. However, this label alone fails to describe the full extent of their impact. The most significant changes associated with wolves do not always result from the number of animals they kill. Instead, many of their strongest effects emerge from how other species respond to the possibility of predation. Large herbivores modify where they feed, how long they remain in certain areas, and which routes they repeatedly avoid. These adjustments alter patterns of grazing, trampling, and movement across the landscape. As these behavioral changes accumulate, they influence vegetation growth, soil stability, and even the physical structure of riverbanks and floodplains. What appears, at first glance, to be a simple predator-prey relationship expands into a network of indirect effects that extend far beyond the wolf itself. The animal becomes one variable among many, interacting with climate, terrain, plant communities, and other species. To understand the role of the wolf, it is not enough to observe individual hunts or population numbers. The broader ecological significance lies in how its presence reshapes relationships throughout the system. To understand this animal, we must understand the system it operates within. In any ecosystem where wolves are present, their position within the food web extends beyond the simple role of a top consumer. Traditional food web diagrams often place wolves at the apex, connected downward by arrows that represent energy transfer through predation. While this representation is structurally accurate, it remains incomplete. It accounts for what wolves consume, but not for how their presence alters the behavior of other species long before any physical interaction occurs. Ecological observations consistently show that prey species do not respond to predators solely based on direct encounters. Instead, they adjust their behavior according to perceived risk across space and time. In environments where wolves are established, large herbivores, such as elk, deer, or moose, reduce their use of areas that increase vulnerability, even if those areas offer abundant food resources. Valleys, riverbanks, and open meadows that limit visibility or escape routes are often used less frequently or abandoned entirely. These decisions are not random. They represent adaptive responses shaped by repeated exposure to predation pressure over generations. As a result, wolves influence how energy moves through the food web without necessarily increasing kill rates. Grazing pressure becomes unevenly distributed. Some plant communities experience reduced browsing simply because herbivores spend less time there. Other areas, perceived as safer, may experience intensified use. This redistribution of feeding behavior changes the flow of energy from plants to herbivores and onward, altering the balance within the system. This effect is especially evident when comparing ecosystems with and without apex predators. In systems lacking wolves, herbivores often maximize foraging efficiency, occupying resource-rich areas for extended periods. In contrast, where wolves are present, foraging decisions involve trade-offs between nutritional gain and exposure to risk. These trade-offs introduce behavioral constraints that reshape food web dynamics. Energy transfer becomes regulated not only by consumption rates, but by avoidance patterns. The influence of wolves also extends indirectly to mesopredators and scavengers. Carrion availability fluctuates based on wolf activity. But equally important is how smaller predators adjust their own behavior in response to wolf presence. Some species reduce activity in areas frequently used by wolves, while others time their movements to avoid overlap. These adjustments further modify interactions lower in the food web, contributing to a more complex and layered system of regulation. Importantly, this form of influence does not depend on constant predation. Even at low population densities, wolves can exert significant behavioral pressure if their movements are unpredictable and spatially widespread. The uncertainty of encounter, rather than encounter frequency, is often the primary driver of prey response. From a system perspective, this means that wolves function as distributors of risk across the landscape. Risk becomes a factor that flows through the food web alongside energy and nutrients. Environmental conditions can amplify or dampen this effect. Terrain complexity, vegetation density, and seasonal changes all influence how risk is perceived and acted upon. In open environments with limited cover, prey responses to wolves may be more pronounced, leading to stronger spatial avoidance. In dense forests, where visibility is restricted, responses may shift toward temporal adjustments, such as altered feeding times. In each case, the food web adapts not through structural change alone, but through flexible behavioral pathways. What emerges from these patterns is a view of the food web as a dynamic system shaped by both physical interactions and behavioral responses. Wolves contribute to this system not only by removing individuals from prey populations, but by continuously modifying how other species interact with their environment. Their role cannot be measured solely in terms of biomass consumed. It must also account for how they reorganize the distribution of pressure within the web itself. When this regulatory function weakens, whether through population decline or spatial restriction, the system responds accordingly. Herbivores expand their range into previously avoided areas. Grazing pressure intensifies in sensitive zones. Energy flows become more concentrated, often leading to vegetation stress and habitat degradation. These changes do not occur immediately, but they reflect the absence of a stabilizing influence that once shaped behavior across multiple trophic levels. In this way, wolves occupy a position in the food web that is both structural and functional. They are not merely endpoints of energy transfer, but active agents in defining how risk is distributed and managed within the ecosystem. Their presence transforms the food web from a static chain into a responsive network, where behavior mediates interaction and balance emerges through constraint rather than force. Across ecosystems where wolves are present, one of the most consistent responses observed in prey species is a change in how space and time are used. These changes do not require frequent predator-prey encounters. Instead, they emerge from the continuous assessment of risk within the environment. Prey animals adjust their movement patterns, feeding duration, and habitat selection in ways that reduce the likelihood of encountering wolves, even when doing so comes at a nutritional cost. In areas of high predation risk, herbivores tend to shorten feeding bouts, rather than remaining in one location long enough to fully exploit available resources. They move more frequently, trading efficiency for safety. This behavior reduces the intensity of grazing in any single area. Over time, these small adjustments accumulate, producing measurable changes in vegetation structure and ground cover. The landscape begins to reflect not where food is most abundant, but where risk is perceived to be lowest. Temporal shifts are equally significant. In many systems, prey species alter the timing of their activity to avoid periods when wolves are most active. Feeding may occur during less optimal hours, such as at night or during adverse weather conditions. When detection risk is lower, these temporal adjustments redistribute grazing pressure across the day and across seasons, further weakening the concentration of impact on specific plant communities. Movement pathways also change. Rather than following direct routes between feeding and resting areas, prey animals adopt more complex trajectories that increase vigilance opportunities or provide access to escape terrain. River corridors, narrow valleys, and areas with limited visibility are used less frequently. Despite their ecological productivity, this selective avoidance reshapes patterns of trampling and soil disturbance, particularly in riparian zones where repeated use would otherwise compress soil and damage vegetation. These behavioral responses are reinforced through experience and learning. Individuals that survive encounters or near encounters with wolves contribute to the persistence of avoidance patterns within the population. Over time, entire herds exhibit consistent spatial preferences that reflect accumulated risk rather than immediate threat. This learned behavior can persist even when wolf activity temporarily decreases, maintaining pressure on habitat use long after direct interactions have declined. From a system perspective, these changes introduce a form of regulation that operates independently of population size. Even without a reduction in herbivore numbers, the way those animals interact with their environment is fundamentally altered. Grazing becomes patchy rather than uniform. Some areas experience relief from browsing pressure, while others are used more intensively. This uneven distribution plays a critical role in maintaining habitat heterogeneity, allowing a wider range of plant species to coexist. Environmental context influences the strength and expression of these behavioral pressures. In open landscapes with long sightlines, prey responses often involve increased spacing and heightened vigilance, leading to broader avoidance zones. In more complex terrain, such as forests or broken topography, responses may be more localized, with fine-scale shifts in movement and timing. Seasonal factors, including snow depth and plant availability, further modify how risk is perceived and managed. When this behavioral regulation weakens, either through reduced predator presence or constrained movement of wolves, prey behavior rapidly adjusts, feeding becomes more concentrated, movement paths simplify, and high-quality habitats are exploited more intensively. These changes reintroduce pressures that the system had previously absorbed through avoidance behavior. Vegetation loss accelerates, soil exposure increases, and the capacity of the landscape to buffer environmental variation declines. Through these mechanisms, wolves exert influence without constant physical intervention. Their role is expressed through the continuous modulation of behavior across the ecosystem. By shaping how prey move, feed, and occupy space, wolves impose constraints that stabilize interactions between organisms and their environment. This form of regulation illustrates how behavioral pressure functions as a powerful ecological force, capable of reshaping landscapes without relying on direct removal of individuals. In ecosystems influenced by wolves, certain areas gradually become underused or entirely avoided by large herbivores, even when those areas continue to offer adequate forage and water. This pattern is not the result of physical barriers or habitat degradation. Instead, it emerges from repeated assessments of risk that make particular locations consistently unfavorable for prolonged use. Over time, these locations effectively disappear from the functional landscape of prey species. Riparian zones, narrow valleys, and open floodplains are among the most commonly affected areas. These environments often provide high-quality vegetation and reliable access to water, but they also limit visibility and restrict escape options. In the presence of wolves, such features increase vulnerability. Herbivores entering these spaces face a higher probability of ambush or pursuit, especially when movement routes are constrained. As a result, even infrequent predator activity can be sufficient to discourage repeated use. Once avoidance patterns are established, they tend to persist beyond immediate conditions. Prey populations do not continuously reassess every location from a neutral baseline. Instead, spatial memory plays a critical role. Areas associated with higher risk are excluded from regular movement routines, sometimes across multiple seasons. This learned avoidance can be maintained even when wolf activity fluctuates, creating long-term shifts in habitat use that are disproportionate to short-term predator presence. The abandonment of these areas alters how pressure is distributed across the ecosystem. Grazing and trampling intensity decline in zones that were previously heavily used. In contrast, areas perceived as safer may experience increased pressure as animals concentrate their activity there. This redistribution does not simply move impact from one location to another. It changes the spatial structure of disturbance, creating mosaics of high and low use that shape plant growth, soil processes, and microhabitat availability. Vegetation in avoided areas responds rapidly to this change in pressure. Reduced browsing allows shrubs and young trees to establish and persist. Ground cover becomes more continuous, stabilizing soil and reducing erosion. In riparian systems, root networks strengthen stream banks, influencing water flow and sediment retention. These physical changes reinforce the separation between used and unused areas, making the ecological consequences of avoidance increasingly pronounced. Importantly, this process does not require continuous reinforcement through predation. Once a location becomes embedded in the collective avoidance pattern of a population, it may remain underused even if wolf density declines temporarily. The system carries a memory of risk that extends beyond immediate ecological conditions. This temporal lag means that the effects of predator presence can outlast changes in predator numbers, contributing to delayed responses within the ecosystem. Environmental variability can modify the extent of abandonment. During periods of resource scarcity, prey may re-enter higher risk areas, accepting greater exposure in exchange for nutritional gain. However, such use is often brief and cautious, insufficient to reverse long-term vegetation recovery or soil stabilization. In this way, risk-based avoidance acts as a regulating mechanism that adjusts flexibly without collapsing under pressure. When wolves are removed entirely or excluded from large portions of their range, these abandoned landscapes are often among the first to be reclaimed. Herbivores expand their movement into previously avoided zones, reintroducing concentrated grazing and trampling. Vegetation declines, soil compaction increases, and erosion processes resume. The rapidity of these changes highlights how closely landscape structure is tied to behavioral constraints rather than physical limitations. Through this lens, habitat abandonment is not an absence of use, but a functional outcome of ecological regulation. Wolves shape the landscape by influencing where animals choose not to be. The resulting patterns demonstrate that space itself is an ecological resource, governed as much by perceived risk as by material availability. This process illustrates how predator presence reorganizes ecosystems by redefining which parts of the landscape remain accessible to other species. As grazing pressure becomes unevenly distributed, plant communities begin to respond in ways that reflect reduced disturbance rather than active protection. In areas where herbivores spend less time or avoid entirely, young vegetation gains the opportunity to establish and persist. Seedlings that would otherwise be browsed repeatedly are able to grow beyond vulnerable stages. Shrubs expand laterally, and grasses complete growth cycles with fewer interruptions. These changes occur without direct intervention, driven solely by altered patterns of herbivore movement. The response of vegetation is not uniform across the landscape. Instead, it mirrors the spatial patterns created by behavioral avoidance. Areas near riverbanks, floodplains, and valley bottoms often show the most pronounced recovery, as these locations are frequently associated with higher predation risk. Reduced browsing allows woody plants to regenerate, increasing structural complexity and vertical layering within plant communities. This shift influences light availability, moisture retention, and microclimate conditions at ground level. As plant cover increases, soil processes are also affected. Root systems stabilize substrates, reducing erosion caused by wind and water. Organic matter accumulates more consistently, improving soil structure and nutrient cycling. These changes enhance the capacity of the land to absorb and retain water, moderating runoff during periods of heavy precipitation. Over time, the physical properties of the soil reflect the absence of sustained grazing pressure rather than any direct alteration by predators. Vegetation recovery further alters habitat conditions for other organisms. Insects, small mammals, and ground-nesting birds benefit from increased cover and plant diversity. These species contribute to additional layers of interaction, influencing pollination, seed dispersal, and nutrient redistribution. As these processes intensify, the effects of reduced grazing propagate outward, linking plant recovery to broader ecosystem function. Importantly, these developments do not require a reduction in herbivore population size. The total number of grazing animals may remain stable, yet their impact is redistributed across space. This distinction highlights the difference between numerical control and behavioral regulation. Vegetation recovers not because herbivores disappear, but because their presence becomes intermittent and constrained. The system responds to changes in pressure rather than changes in abundance. Seasonal factors can influence the pace and extent of plant recovery. In regions with short growing seasons, Even small reductions in browsing can produce noticeable differences in plant height and density. In more productive environments, recovery may be faster and more pronounced, leading to rapid changes in habitat structure. However, the underlying mechanism remains consistent. Altered behavior reduces sustained disturbance, allowing ecological processes to proceed. When behavioral regulation weakens, these gains can be reversed. Concentrated grazing returns to previously avoided areas, suppressing regeneration and reopening soil surfaces. The speed of this reversal often contrasts sharply with the slower pace of recovery, underscoring the sensitivity of vegetation to patterns of use rather than simple presence or absence of herbivores. This dynamic illustrates how stability within the system depends on the persistence of behavioral constraints. Through these interactions, vegetation becomes an indicator of how risk is distributed across the landscape. Patterns of growth and regeneration reflect not only environmental conditions, but also the invisible boundaries imposed by predator presence. Wolves influence plant communities indirectly by shaping where grazing occurs, demonstrating how changes in behavior can restructure ecosystems without direct physical intervention. As vegetation becomes more established in areas of reduced grazing pressure, the physical structure of the landscape begins to change in measurable ways. Nowhere is this more evident than along riverbanks, floodplains, and low-lying corridors where plant roots play a critical role in shaping soil stability. When herbivores limit their use of these areas, the cumulative effects of trampling and repeated browsing decline, allowing plant cover to perform its stabilizing functions more effectively. In riparian systems, increased vegetation density strengthens bank cohesion. Root networks bind soil particles together, reducing susceptibility to erosion during seasonal flooding or high-flow events. As banks become more stable, sediment is less likely to be displaced into waterways. This change influences water clarity, channel shape, and flow velocity, altering aquatic habitats downstream. Over time, these processes can lead to narrower, more defined channels that retain water more consistently across seasons. Soil structure also responds to reduced disturbance. In heavily grazed systems, repeated trampling compacts soil, limiting infiltration and increasing surface runoff. When grazing pressure is redistributed, compaction decreases in avoided areas. Water penetrates more deeply into the ground, recharging subsurface moisture and supporting plant growth during dry periods. This improved infiltration moderates the intensity of runoff, reducing the frequency and severity of erosion events. These physical changes interact with broader hydrological processes. As vegetation slows surface flow, it increases water retention within the landscape. Floodplains absorb and release water more gradually, dampening extreme fluctuations in river levels. This buffering effect contributes to greater stability within both terrestrial and aquatic components of the ecosystem, influencing species that depend on predictable water availability. The reshaping of physical features does not occur uniformly or instantaneously. It emerges through the accumulation of small changes driven by altered patterns of use. Each season of reduced trampling and browsing allows incremental improvements in soil integrity and plant establishment. Over multiple years, these increments translate into visible differences in landscape form, demonstrating how behavioral regulation can lead to structural transformation. Constraints on these processes remain. Extreme weather events, such as prolonged droughts or unusually intense floods, can overwhelm stabilizing influences, regardless of grazing pressure. Additionally, in landscapes where vegetation recovery is slow due to climate or soil limitations, physical changes may be subtle or localized. Nevertheless, where conditions allow, the link between reduced herbivore presence and landscape stabilization is consistently observed. When wolves are absent and herbivores reoccupy these areas more intensively, the physical landscape responds quickly. Banks destabilize as roots are removed and soils compact, channels widen, sediment loads increase, and water flow becomes more variable. These reversals highlight the sensitivity of physical systems to patterns of biological use. reinforcing the idea that behavior, rather than sheer numbers, often determines ecological outcomes. Through these mechanisms, wolves influence the physical environment indirectly by shaping how other species interact with it. The landscape becomes a record of behavioral pressure, reflecting the cumulative effects of avoidance and redistribution. What begins as a shift in movement patterns ultimately alters the form and function of the ecosystem itself, linking predator presence to changes that extend far beyond immediate biological interactions.
The influence of wolves through behavioral pressure is not uniform across all environments, nor is it guaranteed under every condition. The effectiveness of this form of regulation depends on a set of constraints that can weaken, modify, or interrupt the processes observed in more stable systems. Understanding these limits is essential to explaining why similar predator populations can produce very different ecological outcomes in different locations. One of the most significant constraints is predator density. When wolf populations fall below a certain threshold, their presence may no longer be sufficient to generate widespread avoidance behavior. Prey species still respond to direct encounters, but the uncertainty that drives large-scale spatial redistribution diminishes. Risk becomes localized rather than landscape-wide, allowing herbivores to resume prolonged use of high-quality habitats with minimal adjustment to their movement patterns. Spatial restriction also reduces the effectiveness of behavioral pressure. In fragmented landscapes where wolf movement is constrained by human infrastructure, prey animals can learn to identify zones of low predator activity. Roads, fences, and developed areas may function as barriers that concentrate wolf presence into limited corridors. As a result, avoidance behavior becomes narrowly focused rather than broadly distributed, weakening the cascading effects on vegetation and physical systems. Habitat structure further shapes how risk is perceived and acted upon. In open environments with few escape options, avoidance responses tend to be strong and spatially extensive. In contrast, densely vegetated or topographically complex landscapes provide numerous hiding opportunities, allowing prey to mitigate risk through fine-scale adjustments rather than large-scale displacement. In such settings, behavioral regulation may still occur, but its expression is subtler and less likely to produce dramatic changes in landscape use. Temporal factors also impose limits. Seasonal changes in resource availability can override avoidance behavior, particularly during periods of nutritional stress. In harsh winters or drought conditions, prey species may accept higher levels of risk to access essential forage or water. These temporary shifts do not eliminate long-term patterns, but they introduce variability that reduces the consistency of behavioral pressure across time. Adaptation plays a role as well. Over extended periods, prey populations may adjust to persistent predator presence by refining vigilance strategies or altering group structure. These adaptations can reduce the cost of occupying riskier areas, partially restoring access to previously avoided habitats. While such adjustments do not negate the influence of wolves, they demonstrate that behavioral regulation is dynamic rather than fixed. When multiple constraints operate simultaneously, the cumulative effect can substantially weaken system-level outcomes. Vegetation recovery may stall, soil stabilization may remain limited, and hydrological changes may fail to materialize. These conditions explain why some ecosystems show strong predator-driven cascades, while others exhibit muted or inconsistent responses despite the presence of apex predators. The removal or reduction of these constraints can restore the influence of behavioral pressure. In landscapes where wolf populations recover, movement becomes less predictable. Spatial coverage increases, and prey responses intensify. Similarly, reductions in fragmentation or changes in land use can allow risk to propagate more effectively across the system. These shifts highlight the conditional nature of predator-driven regulation. This examination of limits emphasizes that wolves do not impose control unilaterally. Their influence emerges only when ecological and environmental conditions allow behavioral pressure to operate across space and time. The system responds not simply to predator presence, but to the interaction between predators' prey and the structure of the landscape itself. Behavioral pressure introduced by wolves does not operate through a single pathway. Instead, it emerges from the interaction of multiple ecological functions that reinforce one another over time. Changes in prey movement alter grazing distribution, which influences vegetation recovery. Vegetation recovery modifies soil structure and water dynamics, which in turn affects habitat conditions for a wide range of organisms. These processes are interconnected, forming a network of feedbacks rather than a linear chain of cause and effect. As prey redistribute their activity to reduce exposure to risk, the spatial pattern of disturbance becomes fragmented. This fragmentation creates zones of reduced pressure where plants establish more successfully. As plant communities grow denser and more structurally complex, they further discourage prolonged grazing by limiting visibility and increasing uncertainty. In this way, vegetation recovery not only results from behavioral change, but also contributes to sustaining it. The system reinforces its own reorganization through reciprocal interactions. Soil and hydrological processes integrate into this network as well. Stabilized soils and improved water retention enhance plant resilience during periods of environmental stress. Healthier plant communities support a broader diversity of insects and small vertebrates, which contribute to pollination, seed dispersal, and nutrient cycling. These processes strengthen ecosystem productivity in areas that experience reduced grazing, amplifying differences between heavily used and lightly used zones. At the same time, areas perceived as safer by prey experience concentrated use. This concentration limits vegetation growth and maintains open habitat patches. The coexistence of these contrasting zones increases habitat heterogeneity, a key factor in supporting biodiversity. Rather than driving uniform change, behavioral pressure promotes variation in structure and function across the landscape. The role of wolves within this integrated system is not dominant, but catalytic. They initiate patterns that are maintained and modified by other components of the ecosystem. Climate variability, terrain, and plant growth rates all interact with predator-driven effects, determining how strongly behavioral pressure is expressed. The outcome is a dynamic equilibrium, shaped by multiple constraints rather than a fixed state imposed by a single species. When one component of this network weakens, the effects propagate through the system. Reduced predator presence diminishes avoidance behavior, increasing grazing pressure in sensitive areas. Vegetation declines, soils destabilize, and hydrological variability intensifies. Conversely, when multiple components align, even modest levels of behavioral pressure can produce system-wide effects that persist over time. This integration highlights a central principle of ecological organization. No single function operates independently. The influence of wolves is inseparable from the responses of prey plants, soils, and water. Together, these interactions demonstrate how ecosystems organize themselves through interconnected processes with behavioral regulation, serving as a bridge between biological interactions and physical structure. Over extended periods, ecosystems influenced by wolves tend to move toward states shaped by adaptation rather than permanence. Behavioral pressure does not freeze ecological relationships in a single configuration. Instead, it initiates adjustments that unfold gradually as species respond to changing conditions and constraints. The long-term impact of wolves is therefore expressed through patterns of stability, disruption, and recalibration within the system. In systems where predator presence remains consistent, prey populations adapt to persistent risk by refining their responses. Vigilance strategies become more efficient. Group dynamics shift and movement patterns stabilize around predictable avoidance zones. These adaptations reduce the immediate cost of risk without eliminating its influence. Grazing pressure remains distributed rather than concentrated, allowing vegetation and soil processes to maintain the gains established during earlier phases of adjustment. The system reaches a form of dynamic stability characterized by continual movement within defined bounds. Environmental change introduces additional layers of complexity. Climate variability alters plant productivity, snow cover, and water availability, modifying how risk is perceived and acted upon. During periods of resource abundance, prey may afford to maintain conservative avoidance strategies. During scarcity, they may accept higher exposure temporarily, intensifying pressure on sensitive habitats. These fluctuations do not erase long-term patterns, but they introduce pulses of disruption that test the resilience of the system. Human influence further shapes long-term outcomes. Habitat fragmentation, land use change, and management practices affect predator movement and prey behavior simultaneously. Where human activity restricts wolf distribution or reduces mobility, behavioral pressure becomes uneven, weakening system-wide effects. In contrast, landscapes that allow predators to range freely tend to preserve broader patterns of avoidance and redistribution. These differences highlight how ecological processes are mediated by external constraints rather than driven solely by biological interactions. Over decades, the cumulative effects of behavioral regulation influence species composition and ecosystem function. Plant communities that experience sustained relief from browsing may transition toward more complex structures, supporting a wider array of dependent species. Soil and hydrological systems, once stabilized, can buffer environmental extremes more effectively. These changes increase the capacity of the ecosystem to absorb disturbance without shifting abruptly into degraded states. Disruption occurs when key elements of this regulatory framework are removed. The loss of predators often leads to rapid behavioral changes in prey, followed by slower but consequential physical and biological responses. Vegetation decline, soil instability, and altered water dynamics emerge as delayed effects, reflecting the time required for system components to realign. Recovery, when possible, follows a similarly uneven trajectory, emphasizing that adaptation operates on multiple temporal scales. Taken together, these long-term patterns demonstrate that the influence of wolves is neither absolute nor transient. It is contingent, adaptive, and embedded within a broader network of ecological relationships. Behavioral pressure acts as a stabilizing force when conditions allow, but it remains sensitive to environmental and human-driven change. The system's response reflects its capacity to integrate this pressure over time, adjusting structure and function in response to shifting constraints. Understanding the influence of wolves requires looking beyond population numbers and visible interactions. What shapes ecosystems most profoundly is often not direct removal, but the way behavior reorganizes space, pressure, and opportunity across time. In this system, movement patterns matter as much as mortality, and absence can be as influential as presence. Observing these processes reveals how ecosystems regulate themselves through constraint rather than force, and how stability emerges from interaction rather than control. Which part of this system do you find most significant, the changes in prey behavior, the response of vegetation, or the long-term adaptation of the landscape itself? And which other species should be examined next through this ecological lens?